In previous class we have seen two sample t-test. Today we will see chi-square test. All these tests, z-test, t-test and f-tests assumes that the sample data comes from some probability distribution such as normal distribution that has fixed set of parameters like mean, standard deviation. All these tests depends on set of parameters like while calculating z statistic. Here to calculate this z statistics we need population parameters mu and sigma, mean and standard deviations. So this test depends on set of parameters, so we call these tests as parametric tests. In parametric tests, we took a data from sample to infer about the population. In parametric tests, we need parameters and knowledge about the population distribution. Hence here we need summary statistics and assumption about the population distribution. Non-parametric tests makes no assumptions about the parametric distribution when modeling the data. So they are called distribution-free tests. Non-parametric tests does not estimate the population parameter, but it will tell the characteristic of entire distribution. Non-parametric test statistics is defined to be a function on sample. Here we don't need any parameters like mean and standard deviations. Instead, we need entire distribution of data to calculate this test statistic. There might be some kind of data which may not be normally distributed. Such kind of data can be analyzed with non-parametric tests. Categorical data do not normally distributed. So when we are dealing with categorical data, we can use non-parametric tests because it is not following normal distributions. We cannot apply parametric tests like z-test, t-test. So we can go for non-parametric tests. With categorical variables, you cannot calculate mean or standard deviations. It is measured as a frequencies. Chi-square test is a non-parametric test used to determine the relationship between categorical variables. Chi-square test is based on chi-square distribution. So let's see chi-square distribution definition. If Z1, Z2 and so on Zk are independent standard normal random variables, then the sum of their squared values is distributed according to chi-square distribution with k degrees of freedom. It is denoted as Q is a chi-square distributed random variable with k degrees of freedom, or it can be denoted like this. Let's see the explanation. Suppose that Z is a random variable sampled from the standard normal distribution. Like standard normal distribution means its mean will be 0 and standard deviation will be 1. Means we took one sample which is Z from the standard normal distribution. If you square this value, let's square and denote it as another random variable Q. The distribution of this random variable Q is chi-square distribution. Means here we are squaring this Z, so you will not having any negative values. Even if you get some negative value -2, you will square that, it will become 4. So chi-square distribution will have all positive values, means from 0 to up to plus infinity. And it is also non-symmetric distribution. Here we took single z value, so this Q will follow chi-square distribution with degree of freedom 1. This chi-square distribution will be changed based on degrees of freedom like t distribution. If degree of freedom is 1, then distribution will look like this yellow curve. If degree of freedom is 2, it will be like this green line, like that. If degree of freedom changes, distribution will also change. Now consider a random variable z1. This is taken from standard normal distribution, and its squared value will follow chi-square distribution with 1 degree of freedom. means this z value is taken from the standard normal distribution. So most of your data is around mean, that is 0. So the probability for selecting point near to 0 is high, since q value is squared value of this z1. It will also has high probability near 0, and getting 4, 5 or 6, it will be very unlikely. So probability for these bigger numbers will be very less if you take single sample. So if degree of freedom is 1, then chi-square distribution will look like this curve. For example, z1 is 0.5, q will be 0.25. Most of your data will be between 0 to 1. If we take two samples z1 and z2 from standard normal distributions, z1 is 0.5 and z2 is suppose minus 1, then squared sum of these two values will be, that is q, 1.25. Distribution of q for degree of freedom 2 will be look like this curve. If we take three samples from the standard normal distribution, z1, z2 and z3, q will be z1 square plus z2 square plus z3 square. The distribution of q will look like this curve. See here, q values near 0 is almost 0. The probability of summation of all these three values becoming 0 will be very less. It will only possible if z1 equal to 0, z2 equal to 0, z3 equal to 0. Here probability around 1 is high. Summation of all these z values will be around 1. Like that, if you select 4 values, distribution will look like this. As the sample size increases, graph changes. Means if you take 9 values from z1 to z9, summation of these values, squared sum of these values, that is q, distribution will look like this. As the sample size increases, the graph changes. The probability for bigger numbers here 5, 6 and 7, probability for these numbers increases, because if we take squared sum of more values will result some big number. For degree of freedom 1, we have curve like this, means most of the values between 0 and 1, and if we increase the degrees of freedom to 2, then curve look like this green curve. Like that, for degrees of freedom 9, this curve change like this. Let's see the chi-square test. Chi-square test is used to determine the relationship between categorical variables. There are two types of chi-square tests: chi-square goodness of fit test, chi-square test of independence. Computational procedure for both tests is same. First we need to calculate the chi-square test statistic, then determine the degrees of freedom of the statistic. Third, select desired level of confidence. Compare test statistic with the critical value and decide whether to reject or do not reject null hypothesis based on this critical value. It is very similar to our previous tests, z-test and t-test. Let's see goodness fit test. It is used when you want to determine whether the data follow particular distribution. Means suppose you have restaurant, you are expecting that on weekends, Saturday and Sunday, more people will come, and weekdays somewhat lesser people when compared with the weekends. You are expecting, that is the theoretical distribution or expected distribution. Means we have 5 weekdays. On an average, in these 5 weekdays, you will get total 70% of customers, and on weekend within the 2 days, Saturday and Sunday, 30% of customers will come to your restaurant. This is the expected distribution. But in reality, this may not be always true. Means on some weekdays, 65% of customers come on weekdays and 35% of customers come on weekends. This is the observed distribution. Goodness fit test will determine this observed distribution almost is same as this expected or not. It will find that Goodness fit test is a hypothesis test. It uses a chi-square statistic to measure how the observed data is significantly different from the theoretical distributions. Means whether it is same as this expected distribution or is it differing from this expected distribution. It will measure that variation. Chi-square statistic is a measure of deviation between observed and expected values. Very large deviations are unlikely. It is possibly not due to random chance. Means if you have very large deviation between this expected and observation, this large deviation may not be caused by just random chance, but there might be some factors affecting that. If you have very small deviations, like instead of coming 70% of people in weekdays, if 69 or 71, that is so common, but on weekdays if you get 20% and weekends it is 80%, that is very unlikely. So there is some factor affecting that. Small chi-square values or small deviations are very likely, and so they can be attributed to randomness. But how much deviation can be considered as a random chance? Means this deviation can be this 5 or 10 or 20. It can be decided based on critical values. Chi-square statistic. It is the squared sum of differences between observed and expected outcome frequencies, and it is normalized with the expected value. See here, it is like z, sum of all these z values will follow chi-square distribution with degree of freedom here n. Here O is the observed count and E is the expected count. Let's see one example. Test the hypothesis that a random sample of 100 people has been drawn from a population in which men and women are equal in frequency. The observed number of men and women would be compared to the theoretical frequency of 50 men and 50 women. But there were 44 men and 56 women in the sample. We have this data. Here we took a sample from the population. Within that population, men and women frequency is equal. So expected distribution will be for men 50 and for women 50. But in our sample of 100, we observed that 44 men are there and 56 women are there. So observed data is 44 for men and 56 for women. We need to check this observed distribution and expected distribution are same, or this observed distribution is differing from this expected distribution. Here we have some variation. Here it is 6 and here also it is 6. We need to check whether this variation caused due to random chance or not. Here our null hypothesis is men and women are chosen with equal probability in the sample. Means this variation caused due to random chance. Alternate hypothesis is men and women are not chosen with equal probability in the sample. Let's test that whether this deviation caused due to randomness or this probability for man and woman is different. We need to check that. To do that, we need to calculate chi-square statistic. If that chi-square statistic value is too high when it compared with the critical value, we can conclude that difference is not due to random chance. Let's see that. Chi-square statistic is summation of square deviations of observed and expected values normalized with expected values. Observed value for men is 44 and expected value is 50, and their difference is 44 minus 50. We need to take the square for the deviation and normalize that with expected value, that is 50, and add that to square deviation for women. It is 56 minus 50 square by 50. If you calculate this value, it will be 1.44. This is our chi-square statistic. And second step is we need to calculate the degree of freedom. Here we have two groups, one man and woman, but we know that sum of men and women total sample size is 100. So if we know men's count, suppose it is 45, then there is no freedom for women, means it should be 56, because total of this men's count and women count should be 100. So degree of freedom for this statistic is 2 minus 1. It is 1. And let's consider alpha 0.05 means 95% confidence level. We need to find the chi-square critical value for this degree of freedom and this alpha level. Let's see the table. This is the chi-square table. We have degree of freedom 1 and we want 95% confidence level. So our critical value will be this one, 3.841. Chi-square critical value for degree of freedom 1 and alpha 0.05. It is 3.841. Our chi-square statistic is 1.44, which is less than critical value. I mean, suppose a chi-square distribution, if it is like this, for degree of freedom 1, our chi-square statistic is around somewhere here, 1.44, and critical value is 3.841. This is the rejection region. Chi-square statistic is not falling in the rejection region, so we cannot reject the null hypothesis. Means number of men in the population is same as the number of women. This deviation caused due to random chance. Let's see another example. A six-sided die is thrown 60 times. The number of times it lands with 1, 2, 3, 4, 5 and 6 face up is 5, 8, 9, 8, 10 and 20 respectively. Is the die biased according to the chi-square test at significance level 95% and 99%. Given data is this, means die is rolled 60 times. So die has 6 faces. Each face should be repeated 10 times. Means 60 by 6 faces. So each face should come 10 times. This is the expected distribution. But observed values for phase 1, 2, 3 up to 6 is like this. This is the observed distribution. So these are the observed values. Our null hypothesis is the die is unbiased, means these deviations here are by random chance, not due to because of die biased. And alternate hypothesis is the die is biased. These deviations are because of die is unfair. That is the alternate hypothesis. First, we need to calculate the chi-square statistic. So these are our observed values. These are expected values. We need to calculate difference for this observed and expected values. These are the differences. We need to take the square difference values. So it is 25, 4, 1, 4, 0. And if we normalize the square deviations with expected values, the summation of this normalized square deviations is 13.4. It is a chi-square statistic. And here degrees of freedom is n minus 1. Here we have 6 faces. 6 minus 1, it is 5. And if we take 95% confidence level, our alpha will be 0.05. Chi-square critical value for degree of freedom 5 and alpha 0.05. Let's see the table. Degree of freedom 5 and alpha is 0.05. This is our critical value 11.070. This is the critical value. Here chi-square statistic 13.4 greater than critical value. Chi-square distribution with degree of freedom 5 look like this. Chi-square statistic is 13.4 and critical value is 11.07. Means this is the rejection region. Chi-square statistic is falling in the rejection region. So we reject null hypothesis and conclude that die is biased at 95% confidence level. If we change the confidence level from 95 to 99, this critical value will be changed. If you want to test hypothesis at 99% confidence level, let's see the critical value. We want 99% confidence level, means alpha equal to 0.01. Then our critical value would be 15.086. For 99% confidence level, critical value is at 15.086. 86 and chi-square statistic 13.4. This chi-square statistic is not falling in the rejection region, so we cannot reject null hypothesis at 99% confidence level.